Now that you know all about the closure properties of regular language and pumping lemma for regular language, let's go through some exercise problem. Okay, so all these problems are taken from Hopcroft-Hillman, so you can go there, and in fact it's better that you try to solve it yourself, and there are lots and lots of problems. So you first try to solve it yourself. If you can do it on your own, then that's the best thing. But anyway, let me discuss some of this. So here is our first problem. So this language is defined, and the alphabet is just 0. Okay, so the language is 0 to the m, where this m is a prime number. Okay, m is an integer, it's a prime number. So you have to prove that this language is not regular, and the tool we are going to use is obviously pumping lemma. So what was the first thing that we do this as a proof by contradiction? So the first thing is we assume that L is regular, and then arrive at a contradiction here, and then say that okay, L is not regular. So if L is regular, then let n be the pumping lemma constant. Okay, and then we take a prime number p which is greater than n, right? So given any n, you can take a prime number more than that. So do that for n, and then we choose the string 0 to the p. Now 0 to the p, the z is in L, because this is precisely all this 0 to the primes. So this is in L. So that means according to pumping lemma, since the length of z is at least n, so pumping lemma says that if pumping lemma says that if this is greater than this, and if this z belongs to L, so then we can pump z, right? And pump z means that means there exists UVW such that we can pump. So now we show that this cannot be pumped. So that means we consider all breakup. So this UVW, I am not specifying anything here, I am just saying that it's a breakup, but with these two constraints, that this V part should be non-empty and this UV part should be of length at most n. So now if this is the case, everything is 0 here. So this V is so this means that V is equal to what? V is just 0 to the k, right? Now if V is 0 to the k, then for any I, this thing should be in L, but what is the length of this thing? So if you put everything here, so then it will be this expression, right? Why? Because this together, this length of U, length of V, length of W, this together is P, and then if you are applying I minus 1 many V's here, so then you have this thing. So now we can choose I to be anything, and still this should be in L, but now if we choose I to be P plus 1, so then you see that this becomes P plus PK. So that means it's this thing. Now this is not a prime, it's clearly product of two integers. So that means this thing is not in L. But according to pumping lemma, it should be in L. Since it's not, that means pumping lemma doesn't hold. So this initial assumption is wrong, that L is regular. So that means L is not regular. Okay, the next example is this L is set of all strings with an equal number of zeros and ones. So these zeros and ones can occur at any place. So all strings of 0 and 1. So this L is so the sigma that we are talking here is just this 0 1, and this L is language over this sigma, of course. And what strings are here which has equal number of zeros and ones? So they can occur in any place. For example, say you have 0 0, then 1, say 0 1, and then say 1. So this has 3 zeros, 3 ones. So this should be in L. Okay. So all such strings where the number of zeros equal to the number of ones. So in the exam, even we used this notation, this mod 0 or mod 1, right? So it's saying that W is in L if and only if. So if and only if this number of zeros is equal to the number of ones in W. Okay. So now we have already seen a similar example when I'm proving pumping lemma. I'm demonstrating from pumping lemma that that example was the 0 to the I and 1 to the I for all I, right? For all natural number. So we said that this language is not regular. So we have already proved that in previous video. It's not. Okay. So this is somewhat a slightly general version of this. Here also you have equal number of zeros and ones, but now the zeros and ones can be in arbitrary places. It's not like all the zeros occur before 1, right? But here you will see why this closure properties are important. So the closure properties, we proved that if this is regular, then that is regular. If this is regular, then that is regular. So apparently it looks like it is only helpful in proving that something is regular given that you have something regular to start with. But the closure properties are also helpful in proving something is not regular. And here is this example. So we take this L and then we take intersection with this thing. So this is expressed as regular expression. What is this? It's the set of all strings where you have a bunch of zeros and then a bunch of ones, right? Now what is this intersection? So any string here has to have equal number of zeros and ones, and it has to be of the form, say 0 to the I and 1 to the j. So that means this I and j should be equal, right? So what I'm saying is that this is in 0 star 1 star if and only if this is of the form, say 0 to the I, 1 to the j. But this is also in L, so this I and j must be equal, right? So this is also in L, so this means that this I should be equal to j. So that is why this intersection is precisely this language that we are talking about. But now you see by our regular by this closure property what we have. So this language is regular because this is given by a regular expression, right? So this is regular. So this is regular. And now if L is regular, okay, then we know that intersection of two regular languages is regular. So if L is regular, then this intersection will also be regular. So if L is regular, then L1 is regular, right? And this follows from the closure under intersection for regular languages, right? So regular languages are closed under intersection. So, and this is regular. So yeah, L1 is regular if this L is regular, right? But we proved that this L1 is not regular. So that means this L cannot be regular, right? Is it clear that L is regular implies L1 is regular? So that means L1 is not regular implies L is not regular in a contrapositive form. So, and we proved that L1 is not regular, so L is not regular either. Okay, let's go to the next problem. So you remember we defined this reverse thing again while proving closure properties. We proved that regular languages are closed under reversal. Okay, so now so what we mean by reversal? So if you take a string, its reversal is like writing it from the opposite side. So if you have 1 1 0, its reversal is from this side. So you have 0 1 1. Okay, and reverse of empty string is empty because you have nothing. So you reverse it, you still get nothing. Okay. So now the language is x reverse, right? So it's like putting a mirror here. So like you have say a 0 1 0 0 1, I don't, maybe 0 1 1 1, maybe this is your x, and then it's like putting a mirror here, and then taking a reverse. So now you have 1 1 1 0 1 0 0 1 0. So it has a symmetry about this middle line. So this part is and we are considering all such strings. So this string is a palindrome. Okay, but not all palindromes are like this, because this will have even length, right? So this is a palindrome. Palindrome is what? It's a string that if you read from this to this, and if you read from this side to this side, so that will remain same. So this is a palindrome, but it will always have even length. So a general palindrome can be of say 0 1 0 is a palindrome, but this you cannot cast like this. So it's a subset of palindromes. So but anyway, let's prove that this is not regular. Now again we will use pumping lemma. So the first line is if L is regular, let n be the pumping lemma constant. So then we pick some z which is in L and which has length more than or at least n. So we pick our z to be this 0 to the n 1 1 0 to the n, and this is obviously in L. So this 0 to the n is x, and this 1 0 to the n is x reverse. So this is obviously in L. So this is what we pick here, and we will show that no matter how we break this up, we cannot pump it. So we consider a general breakup, but with these two constraints, right? So this v is non-empty, and this uv is of length at most n. So now if we do this, see the first n symbols are n, and this uv is less than or equal to n. So this entire uv is in this part. So that means this v is entirely 0, and v has length k. So v is just this thing. Okay. So that means if I just push another v in the middle, so this is what I get. I get k more zeros. And now you see that this is not of this form, right? It doesn't have this sort of mirror symmetry. It has this more number of zeros. So here you have some n plus k many, and then you have this 1 1. You should have that many zeros here, but here you only have n many. So here you only have n many. So this is obviously not in L. So that means we have a contradiction, and because we assume that L is regular, it should satisfy pumping lemma, but it's not satisfying pumping lemma. That means this assumption is not correct, so L is not regular. Okay. Done. Okay, so let's move to next problem. So again we are talking about reverse. So now this looks very much like the previous one. The only difference is that we have put some W inside, and this W can be any string, but of non-zero length. So you remember this plus means non-zero length, and okay, so this means the union of 0 1. So W is any string of 0 1 of non-zero length, right? And again XXR is this. So again this looks very much like this, so we just inserted W, and the previous language was not regular, so this language was not regular, but this language we will see that this is regular. So why this is regular? See, this X, it's some non-empty string, right? So it either starts with 1 or it starts with 0. It has to be either 1 or 0, because that's our alphabet. There is no other symbol, right? So it is of this form, either 1y or 0y. And this 0, since we said that X is just any non-empty string, so it can be of length 1 or more. So that means 0 can be of length 0 or more. Sorry, y is of length 0 or more. So that means y is this 0 union star, 0 union 1 star. So it can be any string, that means. Okay, y can be any string of 0 1. So now how does this thing look like? Okay, is X W X reverse. So either it looks like 1 Y W Y reverse 1. Okay, so if it is of this form, or it looks like 0 Y W Y reverse 0, either of these two. So it is union of this thing. So we can break this into two disjoint parts. So one which starts with 1, another which starts with 0. These are two disjoint component of this L, and together they their union is L, right? So we have this language from here to here, and then we have this language from here to here, right? And then we are just taking a union. Okay, this union is here. So now you see this, if I take this U W U reverse part here, okay, let's just concentrate on this part, where Y is now any string, so there is a star here, but W is still coming from the 0 1 plus. So if I just define this to be L prime, then what is this part? What is this first component? There is just 1 L prime 1. So this 1 is again written as a regular expression because it's bold faced, right? So this 1 means actually the singleton set so this 1 here actually means the singleton set 1, and this 0 means the singleton 0, and these are concatenation, right? So this thing is precisely this part. It corresponds to this part, and this thing is precisely this part, okay, corresponds to this 0 and 0. So now, in order to prove that this L is regular, it's sufficient to prove that L prime is regular, right? Because regular languages are closed under concatenation. So 1 L prime 1 will be regular, 0 L prime 0 will be regular. So these two are separately regular because of closure under concatenation, and then we have closure under union. So these and these are regular, so their union is also regular. So now what is this L prime? So you see that this L prime, okay, it's some string was 0 and 1, but some non-empty string, because this W itself is non-empty, right? So that means it's a subset of strings of 0, 1, non-empty strings of 0, 1. It's a subset of that, at least that much we know, right? It's a very trivial comment to make. But now you see, this L prime is considering all possible values of y here, right? So now if I take a specific value of y here and allow for all possible w, okay, so this here we fix some y instead of taking all the y. So then whatever we get, so that will be a subset of this L prime. So we fix this y to be epsilon, right? And this epsilon reverses just epsilon itself, right? So that means this thing that I have written explicitly as this concatenation, this is nothing but w, right? It's just w, and w is coming from 0, 1 plus. So that means this is, so this entire thing is actually just this one, right? So that means this L prime is a superset of this, it's a subset of this, that means this is equal to this. And this is obviously a regular language. This is most simple thing. I mean, it's all the strings of 0, 1, I mean all the non-empty strings of 0, 1, right? And this L is nothing but it's almost this all strings, but just 1 and 1 appended before and after, or 0 and 0 appended before and after. So it's just this thing. So it is regular. Okay, let's go to the next problem. So you see the next problem is also quite similar to the previous one. So if you see this expression and if you compare it with the previous problem, okay, it looks very similar. Just instead of xwxr, I have here xrw. Okay. So the first version was this just xxr. We saw that this is not regular. Then we saw that if I insert some w in between, then it becomes regular. And both are quite straightforward. This is extremely straightforward. This is also quite immediate. But now this one, first of all, whether this is regular or not, it's not quite clear immediately what it is. So in fact, if you see the problem in the book, it doesn't say whether it's regular or not. So it asks you to prove this or that. And in this form, the problem becomes quite tricky. So you will see that we need nice little trick to address this thing, and that thing, that nice trick is to take this intersection. Okay, so now this is a regular expression. So this language is a regular language, and since regular languages are closed under intersection and this is regular, so that means this intersection is regular if L is regular. Okay, so if L is regular, then this intersection is also regular. Okay, So the idea is to show that L1 is not regular, so then it will imply that L is not regular. And to prove L1 is not regular, again, so first of all we see that what sort of strings are in L1. Okay, so if you take some string in L1, first of all it has to be of this form. That means it is the 0 1 to the I, 1 0 to the j for some ij. Okay, they are integers. And since it is also in L, that means by this property there exists this x and w non-empty strings such that this z, this thing is of this form. Okay, this form. Okay, so now you see that this x is non-empty, so that means it has at least one symbol. So suppose it ends with some symbol a, so this a is either 0 or 1, so it ends with either, so it's either y0 or y1, whatever it is, it's ya for some a in 0 1. So now concentrate on this part of this string, just this xx reverse. So this xx reverse will look like, sorry, this is a typo here. So this looks like this, right? So x is ya, so then this x reverse is ay, so that means there is a aa in between. Okay, just for this xx reverse part. After that there can be this arbitrary w, this non-empty w, but at least this part contains this aa. So either this is 0 0 or this is 1 1, because this a is either 0 or 1, right? And in this z, in which position does it occur? So suppose your x is of length k, so that means so you have this some string so you have some y or this some x. Where is it? So you have some x, say, so this part is x, and at the very end you have this a, right? And then you have x reverse. So in the next part you have then this a, so this we called y. So up to this portion we called so up to here we have y, and from here to here we have y reverse, right? And now if this a has length k, so that means you have k many symbols here. So this a occurs at position k, okay, and k plus 1. So in this z, so this, and then there is w here. So this entire thing is z, but in z, if you look at this kth position and k plus 1th position, okay, so that should be like this aa, okay. This y can be something, this y can be something, where k is length of this x part, okay. But now look at this z, okay. Z has to be of this form. So let's just look at this z. So you see it has 0 1 0 1 0 1 0 1. So there is no 0 0 or 1 1 until you make this crossover. So until this you finish all this I many 0 1s, and then you start with 1 0. So then you have a 1 and then a 1, right? But then after that you do not have, because after this you again have 1 0 1 0 1 0. So after this you do not have any 0 0 or 1 1. So this thing actually does not contain 0 0 at all, okay? And it contains 1 1 at which place? This here. So you have I many 0 1. So at 2ith place and the next one, okay? So you have this 0 1 0 1 0 1 0 1. So you have 2i many symbols here, okay? And then this 1 0 1 0 starts. So here you have this 1 1, okay? So at 2ith place and 2i plus 1th place for this thing. And then there is no 0 0, okay? In this entire string there is no 0 0, just this 1 1 at this place. So that means if you compare with what we got here and what we got here, so that means this 2i is equal to k, right? This 2i is equal to k. So k is equal to 2i, right? So what was k? K was the length of x. So k is where this x ends. So that means this part, this where this you get this 1 1. So this part should be your x, okay? And after that, I mean, this should be the mirror reflection of this thing. So you got 0 1 0 1 0 1, and then after this your x reverse starts, and that x reverse will consist of, so you have this as an x you get this, so your x now becomes just this 0 1 to the I. So this x reverse part becomes what? So this x reverse part becomes 1 0 to the I, okay? And then you have some w, okay? So this is it. So this z is this, and now yeah. So this part is x, and this part is x reverse. So then you have this w. But this z is of this form, right? So 0 1 to the I and then 1 0 to the j, and out of this part 0 1 to the j, 1 0 to the j. So 1 0 to the I is part of this xr. So for this and this, so this is 1 0 to the I is part of this thing. So this w is nothing but what is remaining. So this w will be this j minus I here. You should have a j minus I here, okay? Just make this correction. So yeah. So this is x, this is x reverse, and then this w is just this thing. So this is the only possibility, and this means that this j is greater than I, okay? Because this part is non-empty. You see that this w is non-empty. So this is positive, so that means this is strictly greater than I. Okay. So this means this entire this argument, so here from here up to this part, so this argument means that if w is in L1, if it is in this intersection, then w is of this form 0 1 to the I 1 0 to the j, such that this j is greater than I and I is greater than 0, because this part is non-empty also, because this x is non-empty, and this part is precisely x. Okay. So this is the implication in this direction, and in the reverse direction also the implication holds, right? So if you take any j greater than I greater than 0, so then this w, sorry, I should have written z here. So if I should have written z here because I'm using w elsewhere. So if z belongs to this thing, then z is of this form, and if this is, so then this belongs to this. Okay. Okay, because this z, we can again break this up like this. Okay. So this part we match with x from here, this part we match with xr, and this remaining part we match with w. So if it is in this form, then it is in in L1. Okay, so this gives you a if and only if condition for a string to be in L1. Okay. So that means this L1 is precisely this language. It is precisely the strings 0 1 to the I, 1 0 to the j, such that this j is greater than I is greater than 0. So this is the language. Okay. So now remember, we said that we will prove that this L1 is not regular, and then this will mean that this L1, this L is not regular. Okay. So how do we now prove that this L1 is not regular? So now we take help of homomorphism. You remember what homomorphisms were? So they were maps from, okay, again. So they were maps from some alphabet to the strings over some other alphabet. Okay. So here I am mapping this A and B. So in fact, this is strings of this to string of this, but this is completely specified by this thing, because in homomorphism we have this property that h of xy is equal to h of x and h of y. So that means if you have some symbols, n symbols, so this is just say h of 1 up to h of this thing. Okay. So now here I define the homomorphism like this. A maps to 0 1 and B maps to 1 0. So it's a homomorphism from this alphabet to this alphabet. Okay. And then we take the inverse of this thing. Okay, inverse of this thing. Now what is the inverse of this thing? So it is the set of all strings over AB such that H map those string to some string in L1, right? So that means this was what? So this is all string say Z in this AB such that H maps this Z to some string in L1, right? So that is the definition of this thing. So what are the strings that can be mapped here? See, you have to match the first two, because this A or B maps to this both maps to this string of length 2, right? So if you start matching from the beginning, so you have to match this 0 1 with this thing. So the first one should be A, then you have to match another 0 1. Okay, so if you do this, then you see that the inverse of this string, so you see that the inverse of this string 0 1 to the I and 1 0 to the j, so you can only have this AIBJ here. Okay, just this single thing. So in general, so if you forgot about inverse homomorphism and all, you go back to that video and brush up. So in general, this inverse can contain more than one string, or it can contain no strings at all. Here it contains precisely this one string. So this is precisely the string over AB, such that this maps to this one under this H. Okay, so this is the only string over AB, which such that H of this thing is this one. There is no other string in over AB such that H of that thing is this one. So this thing is precisely this single thing. So if I do the H inverse of this whole language L1, so I get just this thing AIBJ, where this j is greater than I and I is greater than 0. Okay. So since regular languages are closed under inverse homomorphism, so this we proved. So then if L1 is regular, then this L2 will also be regular. Okay. So that's what closure under homomorphism, inverse homomorphism means, right? So if this part is regular, and then this language will also be regular. So now we prove that this L2 is not regular, which is proved in the next page, and it's straightforward. It's almost same as proving AIBI is not regular. So so we prove that L2 is not regular. So that will mean that L1 is not regular, and since we have this combined with this, when we prove that L1 is not regular, so that will prove that L is not regular. And how to prove that this thing is not regular? It's very straightforward. So L2 is just this thing AIBJ, where j is strictly greater than I. So if it is regular, we use pumping lemma for that. If it is regular, then n be let n be the pumping lemma constant. So we pick this thing. It's in L2 because this part is greater than this. And then if we break this up with this constraint, so we see that this V consists entirely of zeros, right? And its length is something which is greater than 0. So V is just this 0 to the some m. So if I pump this up, so I get this thing. So I get some more number of m's here. So now if you just pick I to be 2, you see that the number of zeros here is at this n plus m, and m is at least 1, right? So that means this part is at least n plus 1, but this means that this string that we are talking about here, the number of zeros in more than number of 1, but here we should have the number of a's less than number of b's. So this string is not in here, so we have a contradiction, and so that means L2 is not regular. So this completes the whole proof. Okay.